Today we are going to see two topics. One is regularization and one is optimization. Okay, but before going to that, again, I'll come to this slide. In the last class, we were talking about this loss functions, and we went through softmax and SVM, and we have seen what are the advantages of SVM over softmax. What are the advantages of softmax over SVM? So those things we already have seen in the last class. Now, just my question is, like initially, like when we were talking about the KNN, and then we found out a lot of challenges, a lot of problems in the case of KNN. And then what I told you that this linear classifier will solve those type of problems. Now, are we able to get those solutions in the case of linear classifier? Have you realized it? Is it like is this linear classifier is solving the challenges what we have seen in the case of KNN? Is it happening? So what was the challenge? What were the challenges in the case of KNN? The first challenge was like it needs a lot of space. So how much space we need in the case of linear classifier? Did you realize it? Okay, let me just give you the answer. Okay, so in the case of linear classifier, what we are doing, we are learning the W. That is the goal. We are learning the W and we are learning the bias. Okay. Now, if I just see, what is your model in this case? Your model is W only, because once your W is fixed, then you are just going to store this W on some edge device along with bias also. You will be going to store it on the edge devices, and then whatever new samples are coming, that will be multiplied with W added, like adding the bias, and then finally you will be getting the class score, or finally it will give you the class level. Okay. Now, do we need to store all training samples in the case of linear classifier after training, like for the testing? Because you know that in the case of KNN, we needed to store all the training images in the memory because those images were required for the testing. Now, do we need to do the same thing here in the case of linear classifier? The answer is no.
No, sir, it's not required. It comes from the training data.
Yes. So actually, you already have trained the model, and you got the W. Now W is the guy who will give you the who will give you the class. Okay. So now no need to rely on the training samples. Now job of the training samples have been done. So only during training you need all the training samples. But once you have fixed the W and bias, no need to consider those training samples. Okay. Now your W is everything. And what was the dimension of the W? If you just recall, the dimension was something 10 into maybe 784. And what is the 784 values? These are the values that we have in the input, because this W was getting multiplied with the X. And X was also having 784 values because that was the input image. And you are multiplying this W with this X, and you are getting 10 values, the score of every class. Okay. So now this W is having size only this much, 10 into 784. And what this mean? If I just relate this with number of samples in the training data, then this is equivalent to 10 images. Because this one is 784 is like the size of one image. So you are storing 10 templates, and those are equivalent to only 10 images. Okay. So in this way, you are reducing the required space to store in the memory in a great margin. Because in the case of KNN, you needed to store every image from the training data. So if you have 50,000 images or maybe 1 million images, you have to store all those images in the memory. But that is not required in the case of this linear classifier. Here, only 10 images. These are not actual images. These are like template that you have learned after doing the training. But this can be seen as a 10 images, because you have this every image is having size 1084. Okay, so it's like we are storing 10 equivalent images in the memory, and that is your W, and these are like templates. So only storing 10 things is solving the problem. So now you can appreciate it. Okay, so the first part is done. So it has reduced the memory requirement in a great margin. Now let us see what happened with the testing time. Because in the case of KNN, we were like your every testing sample was getting compared with all the training samples, because you're finding the difference of the testing example with every training samples, and that's why you required a lot of time while testing. Is this linear classifier is reducing that time or not? So let's see. Now in this case, we don't need to compare with all the training samples. What we are doing here, we're just taking W and multiplying with X. And what is inside the W? Inside the W, we have only 10 templates. That means equivalent to 10 images. So we have only 10 images. And then you are multiplying with X. That means it's also sort of comparison that you are doing. So you are matching your input or comparing your input, this input with every sample here, sitting here. And these are like 10 samples, because we have 10 templates that we have learned. Okay. So what you are doing? You are comparing while testing. You are comparing your test sample with only 10 images, or we can say 10 templates. Now you can appreciate it. So in the case of KNN, every test sample should be compared with all the training samples. So if you have 50,000 or 1 lakh images, you have to compare with every image. Now in this case, you only need to compare your test image or test sample with 10 template image, and that's all. It will give you the score, and you will get the class level. So in both aspects, we are getting advantages. Okay, so that's why this linear classifier said that I'll solve these two problems, and it is solving those problems. So now your testing time is very, very fast, and your memory requirement is also very low. Okay, so I thought of putting this thing because whenever we are moving from one method to another method, we need to compare, and we need to see like how good or what are the advantages in the new method compared to the old method. Okay, so that we should realize. Okay. So now let's go for the topic that is our regularization.
So what will be the disadvantage of SVM? So why we need softmax? That if you can repeat, sir.
Okay, actually here I have only talked about this difference between KNN and linear classifier. Oh, so you are asking separate question, different question.
So from SVM we are moving towards softmax kind of thing, right? Activation function. So there might be some disadvantage as well with SVM. Right? That is my question, sir.
Yeah, so that's the different question. What I said here, so it's different than that question. Okay, because I just I've just given the comparison between KNN and this like K nearest neighbor and this linear classifier.
Understood.
Okay.
Understood.
Or your question is softmax between softmax and SVF? So
Yeah,
that
sir,
we
you can.
already have.
Yeah,
Oh,
yeah.
okay. That we already have seen in the last class. Okay.
Okay, sir, go ahead, please. No
Okay.
issue, sir.
Okay. Please. Okay. So now let's go for one scenario. Suppose we found the W. We got one W, and that W is giving a loss equal to 0. So what I'm saying you, I have given one W, and and this W is giving you loss equal to 0. That means our job is done because we wanted to get loss equal to 0, and you are getting loss equal to 0. So now you'll be happy because this is the happiest case that we wanted to get. That means everything is getting like everything is coming perfect. So for every image, whatever image you are giving, you are getting the right result, and that was the goal from our side. Now, then my question is, if we got one W which is giving loss equal to 0, now is this W unique? So do you have only one W, or we should be having a lot of Ws which can give you loss equal to 0? What I'm saying that I already found one W which is giving loss equal to 0. Can you say like you have only one W in that W space? Because we have the W space where we can choose any W. It's your choice. But somehow we found one W which is giving loss equal to 0, and we got happy. But the another question comes that is this W unique? Now this is the question. What would be the answer for this? Do we have
No, I,
unique W? Sorry, saying no.
yeah.
Okay. So everyone agree with no only?
We can have multiple.
We can have multiple. Yes. How? How can have multiple W's?
Because there are multiple parameters. So basically, any parameter, like sometimes it may increase or decrease, it can become zero. So that's why we can have multiple W's here.
Okay. Multiple parameter, fine. But our parameter is W only. This W is the parameter. W is like you are going to learn. So whatever you are going to learn, that will be called as a parameter. Okay. Or whatever your model is going to learn, that will be called as a parameter. So this W is parameter. So I said that this W is parameters. These are like set of values, and this W is giving you loss equal to 0. Now you got one W which is giving you loss equal to 0. Now my question was, yes, someone like some of you have agreed with this, like someone from your side like said that no, it's not possible. Someone said like, yeah, it's possible to have a multiple Ws. Okay. I think can we do something here so that we can validate this answer? My answer is also no. Unique W is not unique. I go with your points only. So most of you have
Sir,
agreed
like
with this.
we can scale
Yeah.
it up or scale it down.
Yes. So you're close to the right answer. So what if I say 2W? If I said you that W is giving loss equal to 0. So what I was saying that uh, if your W is giving loss equal to 0, what you can say about 2W? Whether it will give the loss equal to 0 or it will give something else.
Loss
It will
zero.
also give loss 0.
Yeah, great. So every combination of the W will give loss equal to 0 only. So when I say that what we found one W which is giving loss equal to 0, that means we'll be having n number of W's, which will give loss equal to 0. Or I should say infinite number of W's. Because this is like infinite space. So W is infinite space. So I can get infinite number of W, which can give loss equal to 0. Okay. So if you get this thing, now my question is, which W we should choose for our purpose? So we have, suppose this is the W space where L equal to 0. So everyone is giving loss equal to 0. So I have, maybe I take W1, W2, like that, all the W's here. I've just put all the W's in a space, in a subspace where loss equal to 0. So every W is giving loss equal to 0. That means I'll be happy with everyone from this. Now my ask is, which W I should choose for my model as a parameters.
So basis vector of that.
Basis vector. How will be choosing the basis vector? But this is not finite space. It's infinite space. You don't know what will be the basis is. So let us assume that. So we are just putting assumption that these W's are perfect. But again, our job is to get some W's which can give you loss close to 0 or equal to 0. And if you're getting that, then it's fine. No? You can also get like very nice generalized W, which can give you loss equal to 0 or close to 0. Now, in this space, every W is giving loss equal to 0 only. Now, which one I should choose? This is just like you have given rasgulla, samosa, all the things. And now, like, thing is like, which one you should choose?
It's a smaller weight, simpler.
What is your name, madam?
It's a Rina Kachi.
Veena. So Veena is saying that we can choose the smaller one. Why? Why not we should choose
So
the
that we can
maximum
get
one?
better prediction. So that we can get better prediction because
Better prediction means like everyone is doing loss equal to 0 only. That means everyone is giving the better prediction only. In
we can
every
also then
case,
overfitting maybe.
Memory is
okay,
less, sir. Memory is less.
memory is less. That's right. Actually, Veena, madam is also saying the right answer. So, uh, uh, okay, so let's choose the smallest one because it needs lesser memory because it is having very low value in that. So W is the matrix, it will be having values here. So maybe these values, all the values are the very, very low values. Okay, so one thing is like if you have low values, then we need less space in the memory because you know that every value should be like every value is like floating point number and then it has to store in the memory. Okay, so that is the one answer because it is having less memory. But let us assume that we have the sufficient amount of memory. We can accommodate all type of W's whatever we have. Then there is no problem of the W. Then there is no problem of the memory. So we can take any W. Okay. So in that case, we are not bothered about this memory requirement. Let us just for some time we just ignore this part. Now, what was the second part? Like, why not we should choose maximum one? And what's the problem with the maximum one? I know that the memory problem is there, but let us ignore that problem. We are not giving attention on the memory problems. We have that space. We can accommodate anyone from this W space. Now my question is, why not choose the maximum one? What would be the problem with choosing the maximum one? If you are not going to choose the maximum one, then you have to tell the you have to give the justification. Why should we not choose? Okay. Okay. So if I choose the maximum one, let us choose the maximum one. Okay. So I'll choose the maximum one, and this is the matrix, and I know that if I'm choosing the maximum, the W, then it will be having all the values very larger. It is having a lot larger values. Okay. Now what will happen? During training, everything is good because your loss is zero. Now you are happy. But while testing, if we go with all these larger values, what will happen if I multiply with x? Suppose this is the testing image, and if I multiply with this, and suppose this x is one variant of the training image. So while training, I have shown some images. These are the images, maybe 50,000 images to the W, so that W will learn, W will experience it, and then W will optimize it. Now your W got the loss equal to zero. Now if you got loss equal to zero, and if you are choosing the maximum W, which is having all the values very large, then what will happen if it gets multiplied with this x? There will be huge effect of this W, because in general, in practice, whenever you are going to train the model, you will be taking x where we'll be having a small values. Suppose you are going to use this x as an image. Then x image is having range between 0 to 255. Every pixel will be having range between 0 to 255. And again, you are not going to give this as it is. What do? You generally convert, you normalize it. So most of the time, you will be normalizing the image or normalizing the input. So after normalization, maybe you will be having a range between all the values. Every value will be between 0 to 1. Now images is having very low values, and you are multiplying this image with W, which is having very large value. So W will oversee. So W will put all its effect. Okay. So W will be having the higher impact on X. Okay. So that means, let me just tell you, suppose you got X, you have shown one X while training. This is the X. Maybe I take, this is the X. And this X has been shown while training. Okay. This is the part of the training samples. And suppose this is the image of me, like, or maybe this image of one person. Now you have taken the image of this person from different orientation or from different angle. So the person is same only, but orientation have been changed. And if the orientation is getting changed, you know that all the values will be shifted. And if the all values are getting shifted, that means this image will be having different values than this image. Indeed, they are referring to the same person only, but they are having different values. And if I go with this while testing, since you know that your W is more powerful, so he will not listen the WX. He will do what he wants to do, because all the power has been given to the W only. So what it will do? It will just W will multiply it with this X, and it might give you wrong class, because this X, it has seen this X while training. So only this type of information if W gets, then it will give you the right class. But if you do the slight change in the image, your things will be totally different, or you will be getting very wrong classes. So you can see taking the higher or larger W, like values, or the taking all the values of the W larger will create this type of problem. So this is called overfitting problem. Okay, so whenever what I was saying, like whenever you uh, go with the larger W, it will create the overfitting case. So what is overfitting case? Overfitting case is the case where your model is doing very good while training. So on every training sample, this, since it has seen all the training samples, and that's why it's doing great, but only on the training samples. But if you go with the testing samples, which is different than the training samples, then it may fail. Okay. So in most of the cases, it will fail. So that means it's doing very good on the training samples, but very bad on the testing samples. And that is your overfitting case. Okay. So did you get this thing? So if you go with very larger W, you will be trapping in overfitting case because W is having too much power because it is having all the larger values. Okay. So what should be the solution? So we should not go with larger W. So which one we should choose now? Just ignoring the space. I'm not focusing on the space part. Which W I should choose that will give generalized model? Larger is giving overfitting. Should I choose a smaller one?
Smaller W.
Smaller W. Great. So I'll be choosing the smaller one. And let us see how good it will perform. So if I choose the smaller one, then what will happen? In the W, again, I have the smaller values. In the W, I have all the small values. These are all the smallest values compared to all the other Ws. And it is getting multiplied with the X. And X is also having the small, it is also having the small values. So both are having the small values. Now no one is very powerful. So I'm giving, I should not say equal power, but I'm giving power to X also. Because X is also the deciding factor. So when I'm going to get the score, then these two guys are the deciding factors. In the previous case, I was giving all the power to the W. Now in this case, I'm not doing that. Your W is also having small values and X is also having a small values. So both are getting like equal power, and now this will be multiplied and you will get the score. So in this case, this will not give you the overfitting problem. Okay. So here, most of the time you will be getting a right result because both are having the power. Okay. So both are having the impact on the final output, which was not there in the case of in the previous case. Because in the previous case, you were just changing little bit in the input and your output was changing drastically because of your W. Because in the W, you had very large value. So just changing little bit here or maybe here will change the result drastically. Okay, because it is getting multiplied with a very large value. And that's why things were like the results were it were affecting the results in a great margin. But in this case, if I change little bit in the x, whenever I'm saying change, that means just maybe the variation of the previous image or the variation of the training image. So if you have x and if you in the training image and if you just little bit you change that image, still this image is belonging to the same object and the change is also very little. So if you have little change, and since we know that w is having also low values or small values, then in the result also, after getting multiplied these two things, there will be no much effect or there will be no much change in the output or in the score, which was not there in the case of taking the larger w, because there like you were just changing small here, little here, it was changing the output in a great margin. Okay, so I'll take the small w because I want this type of scenario, and this is called generalized model because it's not affecting the output. Like whenever we are changing little bit in the input, it's not affecting the output in a great margin. Okay, just affecting the output in a like in the same scale or on the same scale. Yeah. So now we have decided to choose the w, small w, and I think everyone should agree with this. If anyone has any question, please ask. Okay, so I'm assuming that these all the things are clear to everyone. Now, now the thing is, I have this all the w's here, w1, w2, w3, and up to wn. And as madam said that we should choose w1. Now, if I choose the w1 is fine. Just looking here, it's looking very easy that I can choose w1. But in reality, when you are going to train the model, you don't know which w you may face at the starting. You have given this set where everyone is giving loss equal to 0, and you wanted to choose the minimum one, but you don't know where that minimum w is in that space, because here I'm showing he at this place, but this is not guarantee. There is no guarantee that this minimum one will be at the starting only. It may be somewhere here also. Now, how to choose the minimum one from this space? I want to choose the minimum one, but how should choose? How should we choose that? Can we apply the sorting algorithm here? Can we apply the sorting algorithm to sort all the w's maybe in increasing order or decreasing order? Is it possible? And I know that this is the space, and I also know that w1 is the minimum w which I wanted to choose, or I'm interested in that. But the thing is, the position of the w1 is not known. So it can be anywhere in this space. Suppose I started and I got w2, then I got w3, and maybe something else. Now, how should I find the w1? Then I just said that, can I apply algorithm, maybe sorting algorithm, to sort these all the w's? Is it possible? No, because this is infinite space. You can apply sorting algorithm only for the finite space, but this is infinite space. How should we apply that? We cannot apply sorting algorithm. Then what is the solution? The search. But then for how much time you will be searching here? Because this is again infinite space. You don't know where that w1 is. It may be there, maybe at the end also. And is that like this is not finite space. This will go up to infinite. Now it's not easy. So maybe in first sort, if you are very lucky, you will be getting the minimum one. But most of the time, you will be not getting the minimum w from this space just by simple search. Okay, then what should be the solution? Then who is the guy who will help you?
So we can take GCD of non-zero values and divide it.
GCD you can take, but for how many times you'll be taking GCD? You should be also aware that this is infinite space,
Yeah.
not finite space. Maybe you spent 1 day, 2 day, 3 days, still you did not get the best W or the minimum W. That may be possible. So let us go for the solution part.
Can we apply some constant value? Can like multiplying with some constant value and then check with the minimum one?
Yes, you can multiply with the constant value, but again the question again it came on the same page. Like for how much time we should do it? Because
Okay.
again this is infinite space, not finite space.
Yeah.
If there's finite space, then we can do a lot of things. The problem is that this is not finite space.
So is
It
it
should
the
be
case
having
that is why
infinite.
regularization technique should come into picture?
Yeah, yes. So I'm just coming to that part. So that's why I'm motivated, and then I have to go for the solution. Okay. So yes, sir. What you said that is right. So we'll go for the regularization. So regularization is the guy who will help you to get the W with the lowest values. So let us see how it works. So regularization again, like we already have seen in the case of like when we were talking about the classification or the loss, this that was like data loss, like between prediction and ground truth or actual. So that was our that is called data loss. So when we just look the previous, just to recap the previous classes, then we already have encountered this type of loss, and this is called data loss. So what it was doing, it was taking the W, multiplying with the X, applying the F function, like getting the score, and then that score, from that score it was getting the class, or maybe you can also take this score as it is, and you were also knowing about the ground truth at the actual class level. So for every X, while training, you are knowing about the class, actual class. So this was the actual class, and this is the predicted class, or maybe I should say like predicted scores. And then you're finding the loss, like we were applying this VM loss or softmax loss over this. Okay, and this was the data loss. And what I said that we have to minimize it. That was the goal. Till now, we haven't gone for that. How to minimize it? So that part has not covered till now. But somehow we have to minimize it. Okay. So this was the first loss. This was the loss that we already have discussed. Now, since I know that this I cannot find the W with the smallest value, which can give you loss equal to 0 in the previous case. So what I'll do, so instead of going into the W space where every W is giving loss equal to 0 and finding the smallest one, why not we should go for adding this term as a regularization term in the loss function. So since I know that my goal is to minimize the W, my goal is to get the lowest W. So in other words, I can say like this is just like minimization problem over W. The goal is to minimize the value of the W. And at the same time, we also need loss equal to 0, or it should be close to 0. So what I'll do, I'll add the date, I'll be having the data loss. And along with this data loss, now I'll be adding the regularization loss. Okay. So goal of this data loss is to find the W which will give you loss equal to 0. Okay. And now the goal of this particular term will be to find the W which is having minimum values. Okay. In other word, I can say like this term will make the model more generalized. Because when we are moving towards the lowest values or lower values of the W, that means you are somehow trying to minimize the overfitting or underfitting case. Or in other words, you can say like we are trying to generalize the model. So your model is W. So one part is working on getting the W which can give you loss close to 0. At the same time, another part of this is working over W, the W which is having lower value or lowest. Okay. So let's see. Okay. Now I'll ask one more question. Here I'll ask not one question, I'll ask few questions. If suppose I remove this part and I'll saying that just use this part. Okay, actually what I said that this is the whole loss. Okay, so if I'm saying the total loss, that is like your this data loss plus regularization loss, because both the terms should be minimized. This loss also should be minimized and this loss also should be minimized because it is minimizing the W. So that your goal is to minimize the W also, to get the lowest values, and your goal is to minimize this loss also so that you can get the W which can give you loss equal to 0. Now my ask is, can I remove this part? If I remove this part, what type of models or which type of model I'll be getting?
Sir,
Did you?
basically that sigma li of that f of xi. So that is always, this is the W which is already 0. So whatever W we are considering here, it will give the loss 0, right?
The first part is searching the W which can give you loss equal to 0. Actually, previously I shown that we have the W space where every W is giving loss equal to 0. But that is not reality. In reality, you have to also search, you have to also find the W which can give you loss equal to 0. So now what I'm saying that here I have involved two guys. One is this, one is this. Now the focus of this guy is to find the W which can give you loss equal to 0. And the focus of this guy is from those W which has been found by this guy, I have to find the minimum one. Did you get my point or not?
Yeah, I get it. But since in the like above discussion, what I understood is, so we had an infinite space where all the W's were giving loss 0, right?
Yes, I talked this thing. All the
Yeah.
yes.
So now in this we are applying this technique to understand the W which has minimum weight, right?
Yeah, actually,
Which is
yes. What I said that
yeah,
we have this infinite space where every W
yeah,
is giving loss equal to 0. That
yes.
was my assumption. Okay. Now we
So
did
that is
not.
assumption.
Yeah, that is the assumption, and we did not find the W because this is the infinite space. That's why we were struggling, and then we went for the regularization. That will solve this problem. Now, how regularization is working? Now, again, it is not assuming anything because this was the assumption that L equal to 0, this is a space and everyone is giving loss equal to 0. But in reality, again, you have to search this also because you don't know where the loss equal to 0. You don't know which are the W's which are giving you loss equal to 0. So you have to search that also. And who is the guy who will help you. That is your loss function, which we have seen in the previous class. that we find the loss function and minimize it.
Yes.
Once you close to the zero, that in that case you will be getting that W which is the best W, you can say, like which is giving you loss equal to zero. Okay, so loss, that data loss will help you to get the W which can give you loss equal to zero. And then we have added this regularization term, and this term is saying that I'll be choosing the minimum one from that. So whatever this first guy, the first loss has done, now my goal is to minimize the values of the W, because I don't want to go with the larger values of the W, because that may give you the overfitting case. So I want generalized model. So that is the goal of the second guy. But these two guys are working simultaneously. And that's why we have added these two losses in a single total loss. Because these two are like loss only. Again, you have to minimize it. You also have to minimize it.
Okay. But
You have to choose the minimum one here also. You have to choose the lowest values. Here also, you have to choose the lowest loss. Like that is your minimum loss close to zero. So that's why we have added these two terms. Now, what I'm saying you, if I just remove this part, I say that no, I'll not use this part. Can I solve the problem? Can I get the model, good model, just using this? Is it possible?
so, sir, I think ideally it is not possible because since we are depending on the two factors, let's consider K1 plus K2. K2 is lambda R of W and K1 is Li of that. But we just assume that it is giving zero, but we don't know plus K2 will be the deciding factor for that. I feel like that. Yeah.
Sir, as it is clear, as it is clear from the function of these two loss functions, the first one, as you told, it is for it is written here, model prediction should match the training data. So the first is trying to match it with the data. And the regularization, it is preventing it from training on the data, means it is introducing some noise. So the function of second is not to get good results, whereas it is to like over training or to match the data which is in the training set. So sir, second will not help in doing that.
Yes. Yes. Actually, second, if you just see the second term is just giving focus on the W. So its aim is to find the W which is having the minimum values or lowest values. But here the goal of this is not to get the W which is having loss equal to zero. That part is missing here. For getting W which is having loss equal to zero, that is involved in this part. Because this is the actual loss between your prediction and the ground truth or actual. So it is trying to give you the model which can fit on the training data, the first part. That means it will do well, or it will give you the right class every time on the training data. Okay, and that means the same, like you'll be getting loss equal to zero or close to zero. So that part is involved in the first. And that's what is the data loss. So here your model is getting trained on this part only. So you're going to get the best W, or you're going to W which can give you loss equal to zero. That is happening in this part only. The second part is only helping you to reduce the overfitting or just make the values of the W smaller or lower. So if I just remove this part will not solve the problem. Now what this part will give you, if you are just including only this part, what you expect from this part? What would be the at the end, what you will be getting in the W? What will be the minimum value?
Zeros, like non
Zeros, yes, you're right, sir. Zeros. So if I am not giving focus on getting the better model, which can give you loss equal to zero, and I'm even just relying on the W and I'm just minimizing the W, in that case, what will happen? At the end, maybe I'll getting 0, 0, 0, 0, 0, 0, 0. Now, this is, we can say, even not trained model. There is nothing here. It will give you every time wrong result. So this can be considered as an underfitting. But it's not actual underfitting, but in underfitting cases like when like your model is even not doing good for the training as well as for the testing. So in the both case, you are getting very high error. Okay. So this can be considered as an underfitting because this is not doing good for the training as well as for the testing. Okay. So only this part is not sufficient. Only this part is not sufficient. Then what should I do? I should also include this part. I'll also include this part.
Yes. Yes, sir.
Okay, so I'll include it. So, okay, if I include this part and if I remove this part, what will happen? You know the answer of this? If I do not include the regularization part, if just I include this part, this already we have seen in the previous classes. This will minimize the loss. This will give you the W, which can give you loss close to zero. The but problem is that you might get overfitting case, or you may get overfitted model. Because if your W is having larger values, because you are not controlling the values of the Ws. You are just giving focus on matching the output with the ground truth or matching the output with the actual. Okay, so you may get W which is having larger values, and that may give you the overfitting case. So only considering this part will not help you because you might get overfitting case. So that means this part is also required, and that's why we came to this point, like adding this regularization. So now that means we need both the parts. Now my question is, should I add these two parts in equal proportion? Can I give equal weightage to both the part?
No, sir. Sir, the lambda indicates that it has to be adjusted in accordance to the accuracy which
Okay.
is required.
Okay, I put lambda here. Maybe I'll just remove lambda with 1. Is it possible
But
to do?
no, sir, it is not possible.
So
Sir, the
what will happen?
major function, major sir role is of first sir loss function.
Yes. So actually, as he said that the major focus is this part because this is the actual training. This is not the training. This is just for making the model generalized. It's just like when some person is preparing for the ITG exam. So what he will do? He'll give focus on physics, chemistry, math. So that whatever output, like he has to crack the ITG exam. So if he has to crack the ITG exam, he has to give focus more on physics, chemistry, and math. So that's the actual aim. But at the same time, he should be also regularized. So he should also give some focus on game because that is also required for the maintaining the good health. Because good health is required for doing everything good. So when you have good health, then only you can give more focus on the primary goal. Okay. So many things are required, but it is not required in the same quantity. So that guy will give more focus on physics, chemistry, math, and he will give some focus on game. But suppose if he is giving more focus on game also, then what will happen? He may not be able to crack the ITG exam. Okay, so this is the main goal. So your main goal is required. The main focus. That is the main attention. But at the same time, you should also give some focus on this side to make the model generalized. Okay. So let us understand with one toy example. Suppose these are the points, and we have to fit the model here. And you know what? How can we fit the model? We just have to fit the curve. So I'll fit the curve. Suppose I'm fitting this curve. This is one curve which is touching all the points. Now I have just given this curve also, which is touching only 3 points, but it's close to the all other like remaining points. Now, if I ask you which curve I should choose, because this is just training, you're just fitting the again. So neural network is also the fitting something. You're fitting the function. Even in the W, you are fitting something. You're fitting the function W into X. This is also one simple type of problem where we are just fitting all the points. So what
So
I
it is
said that
overfitting.
yeah. So if you go, should I go with the first one?
No, sir.
No. Why no? Because
It's overfitting case.
it's overfitting. It's touching all the points. It's memorizing the point. Instead of learning the boundary, it's just memorizing all the points. And that's not the good thing because it is working very good while training because this is the training phase. But when test comes, at that time it will fail because it has not learned in a proper manner. Now, this second guy is, should I choose this one?
Yes, sir.
Yes, because this is touching all only 3 points, but this is very, very simple model. It's giving you the boundary. It's not memorizing all the points. Instead, it is trying to learn the boundary. Okay, analyze it instead of memorizing it. So I'll give you the example. Suppose just take the same example. Suppose guy is preparing for the ITG exam. Okay, before going to that, let me just give you. This overfitted model can be seen as a guy who is preparing for the 12th standard exam, like CBSE exam. So in the CBSE exam, your overfitted model will work good. Because in the CBSE exam, you just have to memorize all the things from the books. That's all. Because questions will come from the books only. So if you memorize all the points, all the questions, all the answers of the questions, then you will be happy. Because while testing also, everything will come from your book only. Okay. But if the same guy goes for appearing the ITG exam, he will be failed. Because ITG exam wants analytical thinking. So just memorizing the concept will not help you in ITG exam. So if you want to crack ITG exam, you have to prepare in that way. You should not memorize each and everything. Instead, you have to think analytically. Okay. So this can be seen as a guy is preparing for the ITG exam because he will be more generalized. His model will be more generalized. Okay. So he can solve any new questions. But this is the model, or this is the guy who is preparing for the CBSE exam because he will only solve the problems related to the books. If it is coming from outside or it's like totally new question, he will be failed. You can see the similar scenario here. So while testing, you got this, and you can see now this part. These are the testing examples. So while testing, what you can see like these all the examples are close to this because this is very, very simple model and generalized model. But these points are far from this curve. Okay. So that's why what I'm saying that go with the simple model. Simple model is your generalized model. So similarly, like similar thing happened in the case of W also. That's why we were just asking for the W which is having lower values. So whenever I'm saying lower values, that means simple model. Okay. So I don't want to go with very, very complex model. I want simple model because most of the time simple model works. And that gives you the more generalization on the testing data. Okay. So I think if you understood that part, so again, so I will not give equal weight to here. So this is called hyperparameter. So you have control over this. So you can change it. So whenever, like you have to just play around this. So you just see like which value is suitable for the particular problem. Okay. So that is one thing that you can do. The other thing is like nowadays people are also making this lambda as a parameter. So maybe most of the time we are getting lazy. So every time like we don't want to play around this lambda. So what we do, where we just put this thing this lambda to the model only. So model itself will decide like which lambda I should choose. So now everything we are just giving to the all the things, all the responsibility we are just giving to the model only. Okay. So this lambda most of the time we take as a hyperparameter. So whenever I'm saying hyperparameter, that means we are fixing the values. We are just playing around these values. And whenever I'm saying parameter, that means your model is going to decide it. So nowadays people are also using this as a parameter also. Like model itself will decide like which value I should choose. Okay. So I have talked about this part before. We also have seen this part, but I haven't talked about this R, like which function I should use here. So we have different type of functions that can be used here. So we have L2 regularization, we have L1 regularization, we have elastic net, we have a lot of things, a lot of functions that can be applied here. Okay. So now if I just see what is L2 regularization, so L2 is just like squaring all the values, all the, please mute yourself. Okay. So L2 is like just square all the values. So we have matrix. This is the matrix. You got the W, and now you have to minimize the whole W. So what we'll do? Just take the square of each value here. Square of each value, sum it, and this sum should be minimized. So that is like L2. In the case of L1, what we do? We just take the mod of every value here, and then sum it. Okay, and that should be minimized. So L2, again, L2 is having some limitation. L1 is also having some, because you know that every method will be having some limitations and some pros and some cons. So then elastic net comes and it said like, why not we consider the pros from the L1 and L2? So it has just combined L1 and L2. So you can see like this is the combination of L1 and L2. This is L1 and this is L2. Okay. So let's see the, okay. Apart from like these are like simple regularization technique. Apart from this, you can also go for complex regularization technique, and those are dropout, batch normalization, stochastic depth, fractional pooling, etc. So some of these will be also seeing in our class, maybe in later classes. Okay. So the goal of the regularizer is to work on the weights and make the model simple so that it will work well on the test data. That's the job of the regularization. Okay. Now let's see one example. Suppose I have given you this X, I have given you this W1, and I have given you this W2. Now I'm giving you two Ws, W1 and W2, along with X. And what we have done? We calculated this W1 into X. Again, this multiplication for getting the score. So W1 into X and then W2 into X. Now our goal is like choose W from these two Ws. So we have to choose one from this. Okay. So what I'll do? First I'll check like how much, like first thing is like you have to see like how much, what is the performance that you are getting. Okay. Suppose one is giving you high accuracy or higher accuracy, then you will go with that only, because first priority should be given to the accuracy or performance, or we can say the data loss. Okay. But are giving you the same performance, then there will be tie, and then you have to go for the regularization. First we'll focus on the data loss, and once we got the same as like when I said that the job of the data loss is to get all the W's which can give you loss equal to 0. Now, if that part is done, then the goal of the regularization is to choose the minimum one from that. Okay. So here, this example is for that only. So let us see like whether these two W's are giving the same performance or not. So if I multiply W1 into X, W1 into X, what value I'll be getting? 1. Row of W1, column of W2, only this value will be multiplied with this, remaining will be 0, so you'll get 1. Similarly, if I multiply W2 with X, so what I'll get? 0.25 plus 0.25 plus 0.4 times, it will give you 1. So in both cases, W1 into X into and W2 into X is giving you 1 only. Now the question is, which one I should choose? Now let me just give you a regularization function that is L2. So I'm giving you L2. Now let's take the L2 and decide which W you should choose from here. You have two W's, na? Now which one everyone is giving the same result. That means everyone is giving you loss equal to 0. In this case, everyone is giving you 1. Now which W you should choose using L2 regularizer? Can you give the answer? It's a very simple question.
I think double 2.
So you're saying W2. Why, sir?
That because it is uniformly distributed, right? So you will have some value for each and every elements of X.
Okay. Actually, we are going one step beyond. Okay. Before going to this distribution, uniformly distribution, you have to apply this L2. And you know that you have to choose the minimum one. And you also know what is the formula of L2 regularization. So how will you apply the L2 regularization? Yeah, please go ahead.
Sir, mean square error summation should be least.
Yeah, the regression value should be low. Na? Your goal is to minimize the W. You want lowest value in the W.
Yes sir. तो सर जब W1 का स्क्वायर करेंगे तो 1 बनेगा, जब W2 का स्क्वायर करेंगे तो समेशन करके भी वो लेस बनेगा.
That's why I'm asking like which one we should choose.
Sir, W2 obviously sir, because of that.
Yes. So what you will do? You have to apply like performance wise. Everyone is giving the same performance. Now what I'm saying that you apply the regularization and then choose the minimum W. So what you will do? You just apply the L2 because I said that you apply L2. So apply L2 over this W1. So if you apply on W1, what will be the output? 1 0 plus 0 0 0 1 square plus 0 square plus 0 square plus 0 square. This will give you 1. If you do the same thing for W2, so you'll be getting 0 to 5 whole square 4 times plus this plus the same plus same plus same. That means 4 times. If you multiply it, what will be the value? 0.25. So if you are applying the L2 over W1, you are getting 1. And if you are applying the L2 over W2, you are getting 0.25. So based on the regularization term, you should choose this because this one is giving you the lowest values and that you want to get. Okay. Now, this is about L2. Now, what if I change this L2 with L1? So if I say you like apply L1, what you will do? What you will choose from this? Now apply L1.
Both will give same.
Yes. So if you apply L1, W1 again mod of 1 plus mod of 0 0 0 0 you will get 1. For W2 mod of 0.25 4 times. That will also give you 1. So both cases are giving you 1 only. So there is tie. Okay. Now you can choose anyone from this. Okay. So you can see like regularization term, the regularization function will change this like for choosing this W and W2. Okay. So if you are taking L2, things are different. If you are choosing L1, things are different. Okay. So if I go with L2, you will be choosing the W2. If you are going with L1, you can choose anyone from this. But let me just tell you, most of the time, L1 will give you sparse matrix. So whenever I'm saying a sparse matrix or sparse vector, that means most of the elements in that matrix will be 0. Okay. So in this scenario, you are getting same, but in most of the scenario, if you go with L1, it will prefer this over this. So it gives more focus to the sparse vector or a sparse matrix. Okay. But if you go with L2, L2 will give more focus on this compared to this. So your L2 gives more focus on dense matrix. Dense means like you have most of the values are non-zero, and they are like it's like spreaded in the matrix. Okay. So what L2 does? L2 choose the W or L2 spread out the weights. So it will not give focus on the sparse. Instead, it will give focus on the dense, and all the values will be spreaded. So here you can see like everyone is having weight. Every value is having some non-zero value. But in the case of L1, you can see like 3 of them are not having non-zero values. So it's not giving or it's not spreading the values in that matrix on that vector. Okay. Now my question again here is, you have seen like what is happening using L1, what is happening using L2. So which one I should choose for solving the problem statement? You know that your L2 is giving it's giving more weightage on the matrix which is having spreaded values like non-zero values most of the in most of the elements or in most of the indexes. But your L1 is giving more focus on the sparse matrix or a sparse vector where we have most of the values are 0. Now the thing is, which one you should choose for your model? Should I go with L2? What you can like? What do you say? Whether L2 is better than L1 or L1 is better than L2?
Sir, L2 would be better than L1.
W2 is having exact representation of the training data.
Very right.
Like user.
Very right.
Yeah, because as L1 like focuses more on the zero values of this sparse matrix. So L2 would be better. Yes.
Yes. Yes. So some of you have given answer that we should choose L2. But
Sir, as you
Yeah.
were giving a concept of overfitting. So, sir, W1 shows 1, 0, 0. Sir, so 0, 0, 0 means good fitting there, but 1 means that it is showing absurd value here. Whereas W2 shows consistent value like the residue or the distance between the estimated point and the actual point is less. So W2 seems in the range, but W1 in certain points will give you absurd value.
So what you
That-
prefer to go with?
W spread out value, because this is what we require in a model.
Okay, fine. Actually, the answer is you can choose anyone. You cannot say like L1 is better or L2 is better. It depends on the problem statement that you are solving, or it depends on the images or examples on which you are working. So let me just give you the example. Then you will be able to realize it or appreciate it. Suppose I have given the image. This is the image, and in this image, I'm going to classify it. And suppose this is the image of maybe one of you. Suppose this is your this is your image here. This is the full image, but the object, the person is here only. Okay, that means in this whole image, most of the parts are background. That means that does not belong to the your actual object. But your goal is to classify this. What is the class of this object? So what you do? You generally convert into vector, and then you give to the you multiply with W. Now, whenever I'm saying you are multiplying with W, that means every value of the W is getting multiplied. Like this value will multiply this value will multiply this. So you are multiplying every value of W with the corresponding value of the X. And then you are getting the output. You are getting the score. You are just summing all these things and you are getting the final score. But do you feel that in this case, we have to give attention on every values here? No. Because our area of interest is only this much, na? It means we are going to classify it. We don't need to give attention on these parts. Maybe this might not be useful for us. So this might be noisy thing. So this may change the result, or this may affect the result. So why we should keep focus on these parts? So if you have this type of scenario, then your L1 may be good, maybe better than L2, because you want a sparse vector only. You don't want to give focus on every part. What your W is doing? W is giving focus on the input only, na? Every value is getting multiplied with the input. That means you can just see in the previous example what you were doing. You were multiplying this W with X. This value is multiplied with this. This is getting multiplied with this. This is getting multiplied with this. This is getting and what is this? This may be the representation of the image, because you might have converted your image into vector. And you know that only this much part is the useful part from the image. Then why should we give weightage to every part? So in that case, your W may be preferred over this L1 may be preferred over L2. But suppose if you take the scenario when
Depends
we
on
have yes. Suppose you have scenario when we have this image, this considering the full. This object is considering the full image. It's like in this case, maybe you will be preferred to go with W2, because in whole image you have the object and you want to classify this. So this full image is covering this object. So if you have this type of scenario, then you might prefer to go with L2. If you have this type of scenario, then you may prefer to go with L1. But again, how to know like what is the scenario we have in the data set? Because every time you need to go with the data set, you need to see the images, how your images are there, what type of images you have, how it is looking like, what is there, like whether this is like just containing the full portion of the image, or it's just containing the only some portion of the image. So this is again tedious task. Then what we do, because we know that for this type of things we are very, very lazy. Okay, so what we do now, we just put all the responsibility to the models only. So that's why this elastic net came, and it says that you just take the combination of both with the weight. So when I talked about the elastic net, so why not take combination of these two? So model itself will decide like which regulation technique I should give more focus, which regulation technique I should give less focus. That means whether I should go with a sparse or I should go with dense. So now we are just putting all the responsibility to the model. Okay, so we are done with the regularization. So now the next part would be optimization. So we haven't talked about who will give you the or how to choose the best W. I just said that we have to minimize the W. We have to minimize the loss. But then how should we minimize the loss? What is the process? And by while minimizing, how should W be updated? So that part we are going to see in the next class. Now we will be playing around optimization or choosing the best W. Okay, thank you. Any question? Otherwise, I'll stop. I took 5 minutes more, so sorry for that.
No issue, sir.
No, if no further question, then I'll stop. Thank you, sir. Thank you. Thank you.